So yes, I put line energy models because there are some which are almost equivalent but not equivalent. I will focus only on the Aviles giga case today. Okay, so it is, but the proof is the same anyway. So, okay, we have that omega is okay, we say bounded smooth connect domain in R2. Okay. Okay, maybe we can fix a small parameter epsilon and consider these functions used by Aviles and giga. Okay, which are the following. So there is 1 over epsilon, the integral of 1 minus equation square plus epsilon, the integral of omega equation square u square. Okay, so there are 2 parts. The idea is that we will let epsilon go to 0. So we expect that in the limit we get solution of the differential equation, so the modulus of the gradient of u equal to 1. And we want to understand if so the behavior of minimizers of these functionals as epsilon goes to 0. So okay, let me fix some boundary condition. Okay, u, in order to make sense, we take u with the 2 derivatives in L2, and we consider u equal to 0 as the boundary. Okay, so the goal is to take u epsilon minimizer of epsilon on this omega with this boundary condition. Let epsilon go to 0 and understand the behavior of this minimum. Okay, epsilon as epsilon goes to 0. This is what we want. What we want to do. So there are okay, maybe 2 main questions for this specific model, which are not complete yet. So the question is, okay, the first one, is does the epsilon converge to some solution this is solving the equation. This is what we write, and if yes, which solution can be characterized in some way. If this procedure selects some specific solution of the differential equation or not. Okay, the answer is so the answer is yes for the first part. Essentially, you have to prove that that sequences okay, of minimizers of solution with equibounded energy are their gradients are compact in some cases, right? In order to go to the limit and get the use of the equation. This has been done okay, independently. There are two works that are fundamental in this topic by Ambrosio De Ellis Mantegazza and another by De Simone con Müller and Otto. Okay, and okay, so the answer is yes to this question. And okay, what is still not known is which solution we select by this procedure. Okay, and okay, related to this, the second question is if okay, we have a candidate, we have a particular solution of this equation. It is the viscosity solution. It is the distance from the boundary. And okay, in which cases does this procedure select the same solutions? Does u epsilon converges to? So let me write like this. Okay, here we can take. Okay, if you take u or minus u, it's the same energy. But let me write like this to say that okay, any limit point belongs to is one of these two functions. Okay. So the answer in general is no. There is an example by Rado and Merlet when omega is non-convex. So at least if omega is convex. So these are the two questions. Okay. This is like a general remark. Okay, if you want, the result of today is a bit related with the second, but it's very particular. Okay, so today I will, okay, let me introduce this result by Chaban, Orto and Cartana. That is what we would like to make more quantitative in the end. In two. Okay, so if we have the sequence of energy, so if it is okay, it answer in some cases, but it is also a liquidity result. So if F epsilon, the epsilon converges to 0, okay, and omega is as before, bounded, smooth, and connected, and then you have the following indicator. So omega must be a leaf, so the only domain for which we have this sequence of is the ball, and then okay, and u is the distance, plus or minus the distance. Any limit of u epsilon belongs to plus or minus the distance in the boundary. Okay, so okay, so this is the theorem, and it is for it works only for zero energy in the limit. Okay, and let me briefly discuss the strategy of the proof. Okay, first they provide a kinetic. We have this kinetic formulation. Let me write the title, and I will say what it is. Kinetic formulation for zero energy states. Zero energy. Okay. So what I mean, okay, it is convenient. For the sake of this talk is only some notation more, but okay. So let me consider the rotated gradient of u epsilon. Okay, and a zero energy state, we assume that the energy, okay, as before. Okay, we assume that the energy is vanishing as epsilon goes to 0, and we take n equal the gradient energy of the limit u. Now we don't know yet that it is the limit or not. It's just some limit point of u epsilon that we know it exists by the previous definition compactness result. So we can introduce this kinetic function E that goes from omega times one dimensional S1 R divided by 2 pi z. And it takes values in 0, 1. And it is defined in the following way. So you take a point of E of x is equal to 1 if n of x dot e to the ix is positive and 0 0 y. Okay, so it means that okay, we added a variable. Now we have this additional kinetic variable s, and if you have our set omega, our point x here, and maybe we have this m of x, which is one normal vector. The modulus of n equal to 1. Okay, so for each point x, the function t of x will be the characteristic indicator function of this alpha circle of direction. Okay, so for these values of s, so the one which determines direction, which are, let's say, almost parallel. Okay. In this alpha circle will be equal to 1. So e of x here will be equal to 1, and here will be equal to 0. So at every point we select alpha circle of directions. And okay, this is only the definition. What they prove is that if m is at zero energy states, so the limit of vanishing energy u epsilon, then it satisfies these kinetic equations. satisfies e to the I dot gradient of 3 equal to 0. Okay, so this is a transport equation. It's very simple. The vector field depends only on this variable. The derivatives are only in the x in the x direction. Okay, so what does it mean if we? What does it imply? So, okay, we have taken. Okay, I want to do something like here. So here it is x. Here is m of x. Now let us take a direction where s, so the key of the x is positive. So, for example, this can be e to the I hat. So this equation is saying that if we take in this direction, so along this line, okay, we have that e is constant. So it means that along this line, e of x is identically equal to 1. Okay, so because it was 1 at the point x. Okay, so what does it mean that it is identically equal to 1? So if you take another point on this line, what do we know in this point about m of x? And we know that m of x must be in this alpha circle, right? Because m of x times e to the AIS must be positive. Okay, so we don't by this equation, by only this information, we cannot detect the value of m from this point, but we can exclude half of the possible values. So this is the information that we have along each characteristic from this equation. Okay, so now let me say quickly how this constraint that omega must be at this. Okay, so the second part, if you want, is the analysis of characteristics. Okay, you have to use this argument to get some information on the geometry of this domain. So we have, okay, since u restricted to the omega is equal to 0, we have that our rotated gradient will be perpendicular to the normal. Okay, the normal is equal to 0. Okay, and the idea is that this constraint plus the kinetic equation. Okay, so this kinetic equation, so this information that we have implies that omega must be like this. Okay, to see it, just let me write a kind of a short explanation, and then we will reuse this argument later. So the idea is that if so, let me just write the idea. So if the proof is by contradiction, if omega is not a disk, then we can find x belonging to omega such that t of x is not the characteristic, the indicator function of alpha zero. Okay, but we know that E must be the characteristic. Okay, here it is a point. You should find a set of positive measures because everything is defined almost everywhere, but just skip it. Okay, and how can we provide a point like this? Okay, suppose that here is x1. This is m of x1. Okay, it can be in this direction or the opposite. We don't know. And take other points. Okay, we take the normal. I hope that's the order. Okay, there seems almost. Let me try. Okay, we take the three normals here. And how can we build with this information of the boundary, some point that is not good for this to get a contradiction. The idea is to take the center. Okay, any point there, but you can take the center of the in circle of these three lines, which assume they are not concurrent. Okay? If it is not a circle, we can find three lines which are not concurrent. And okay, so here we take this direction. Okay. In this direction, M a key of xs is positive, right? Because here it is in the alpha circle detected by the boundary condition. And it is the same also for the others. So we have these three directions. Okay, maybe it's not so okay. It's a point, but the point is that at this point we will find three directions not belonging to the same alpha circle where k is equal to 1. Here it is equal to 1, here it is equal to 1. So these 3 points do not belong to the same alpha circle, so this function cannot be the characteristic of alpha circle. So we cannot select any values of m such that these are at least one of the 3 must be 0. Okay? So this is more or less the geometric argument behind this. Okay, so what we would like to, or the theorem we would like to present a bit more in detail, but no, is yes.
Which sense limit?
Limit, okay. Yes, it is, for example, in L1 for the gradients. Yes, the gradient of U epsilon converts to the gradient of U in L1. Okay. You can get even some better exponent, and then it depends on the compactness estimate you can prove. So if you know that a sequence has equibounded energy, you can prove that the gradients are compact in some empty spaces, in particular in L1.
So you say that if it's not, if omega is not a disk, you can always find 3 points. So with this property and such that they are not all of them in the same alpha circle.
The only thing that you need is that you have the three normals to not you do not are concurrent. You don't pass to the same point. Okay, if you have a circle, they are all radial.
That's clear.
If it is not a circle, they don't.
You always find that a triple, but you don't need this triple are somehow distributed in.
Okay, yes, in general.
Okay, this section of the uses a bit that they are somehow not all the
yes, okay.
What can happen?
Yeah, but in the other case, you will use instead of the entering, the exiting ones.
Okay.
Work anyway. Yes. Yeah. Okay, so the theorem. Okay, it is that we take the same assumption as before on omega in order to fix the radius of the ball. So the scale we just assume that h1 of the boundary is equal to 5, so the radius 1. Okay, and then we put here the curvature of omega is less or equal than some capital K. Then there exists a constant depending on such that we can control this distance of omega from being a circle. The distance square between omega and the ball. Okay, let me write the infimum over of the ball of radius 1 sin independent star. So we put the ball in the best position. Okay, plus the integral in the boundary, and now we take the difference between the normals. So the normals of And what will be the normal of the circle? X minus R divided by the multiple of minus R. This difference in 2. Okay, square. And this is therefore equal than C, the linear, as epsilon goes to 0 of the infimum. Okay, on the infimum of epsilon on omega. Okay, so we take the meaning, let us call given lambda of omega squared. So this, which is, we don't assume that it is 0 now. It can be a finite value, and we prove that we can control the distance of our domain from being a circle by this quantity. Okay, if it is 0, we get exactly omega instead of. Okay. Okay, and then we can also obtain an estimate of the solution from the distance. Okay, it is done on the gradients, but this is the rotation.
So this infimum is in front of both terms.
Yes. Yeah. So this infimum means that you just put the ball in it's invariant by translations. So you have to put the ball in the best position.
Clear, maybe it's completely stupid question, because I'm infinite, there is the first term and then there's the second term, integral term. So
Yes.
is it clear? Probably it's not true. So a naive question is like the optimization for the sum of two terms, is it the same over x0? Is it the same as optimization over the first term? No.
It's not clear that it is the same.
It's not clear. You don't have like an immediate example.
No, I don't.
I mean, of course, but only that is.
Apart from the yes,
I mean, the right-hand side is another thing. I mean, this is your domain, the importance of your result. But just looking at the left-hand side, and can I find an example?
Okay,
Said that fitting just with respect to the boundary, the Hausdorff distance between the boundaries.
Also the infimum of plus the infimum. It is too many. You can also put infimum plus infimum, which is something which is possibly smaller. Is in general small. I think it can be. Yes. I don't know if I answered. So I think that the optimization for this is not the same as optimization.
Yeah, but do you see an example immediately? No set. Optimizing just the distance between the boundaries is not the same as fitting with this other thing. Well, okay. Never mind.
Or I can read the same file. Okay, so we have this here. We have okay, again it is okay, this for alpha belongs to alpha minus 1 because it is and so this is exactly the rotated gradient of the distance function, and it can be the distance or minus the distance. Okay, so this result is sharp in the sense that we cannot improve for sure the constant that we put here, so we cannot take anything smaller. But okay, it could be that this can be. We don't know. Okay, and the other is probably not. It's probably not. Okay, there are. Let me mention that there are also other results of this kind by Laurent. There are two interesting results. They deal with or they put some additional constraint on the domain. Maybe it is convex, or otherwise, and on the initial data. So here we have that they fix the time is equal to the tangent to a fixed direction instead of both of them, okay, of only this one.
Can I verify? Is it clear? How about the other inequality? If I wanted that cream soup of this infima f epsilon is less or equal than what you have in the right hand, what is in the left hand side. Is it all obvious or?
They are
Because we have like one-sided equivalence, right? It's the statement, the Otto, the Jabin Otto per femme.
yes.
Yeah, so the other is the other inequality also true?
So if
So
you
the
take
different constant.
something which is closer to the circle, you can.
But if I know that the left-hand side of this infima
is
yeah,
is small. Okay. 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 This is okay. Yes, maybe with some other concept. But what I would try to take the distance from the boundary and evaluate the energy of some modified version of it, and see. If
so you think it is true.
Okay, no, because I don't think it's optimal in the power. So like this, it should not. But this one. I'm not sure. I never.
Okay, could you explain what does it mean this for a square? What is your result for a square?
Okay, the square is a bit.
Because I don't see what. I mean, if it's a perturbation of the circle, I see the interest, but otherwise, what's the interest of it?
No, the interest. No, it's okay. It's only for this energy small.
Yeah, okay, but then better to say that it's a because otherwise, what's so I mean, really, for square, what
is something a solution which is the vortex. It's the stability of being a circle. And if you are far from it, we cannot say. No, for so what you can do is okay by this. Okay, not from this result, but by doing this analysis, you can provide a lower bound for the square also, but it doesn't match the upper bound. So you can provide a lower bound if it is more better than just testing all the entropies at the boundary, and because this kind of thing maybe will be more clear. But this will okay. The analysis that I'm going to explain will encode all the entropies in. But okay, you cannot say that the lower bound is not, for example, the energy of the distance. So okay, as it is only a result interesting close to us here. And okay, so the idea now is that we would like to more or less make quantitative the previous argument. And in order to do so, okay, the first part is okay, the kinetic formulation. Kinetic formulation for okay, finite energy solution. Finite energy solution. Okay, this has been okay. Let me explain a bit what I mean. Now that the limit of the energy is not zero anymore, can be finite value. Okay, so we have that E epsilon converted to some u, and if we have a equivalent energy, and the Q epsilon converges to some u, we have the rotated gradient also converge to n, with the rotated gradient. Converges to some vector field n, with the rotated gradient of u. And now the kinetic the kinetic function T is the same as before, the characteristic of alpha circle determined by the vector m of x. And then there is this value is also what by permanent term, but okay, what is more convenient here is this more recent version obtained by Giraldin and Lamy. let's say that if n is like this, a limit. Let me denote this way. I will not say anything about the limits. It's just the limits of sequence with equivalent energy. If n belongs to Elio for omega, then there exists a measure. It is a finite measures on omega times such that is like a finite measure. Such that e to the of the gradient of t is equal to the derivativeness of the measure. Okay, so again, as before, we have a transport equation. Okay, but the right hand side, instead of being zero, is a derivative of a measure. So it's quite a bad source. And okay, then it is this sigma is related to this lambda of omega. So if you choose a property with this sigma, okay, the only freedom you have is up to function of s, up to function of x, which are derivative, both derivative in SSC. Okay, so if you choose it correctly, you can you have that the mass of this measure is up to some constant, less or equal than our the limit at epsilon goes to 0, and we take the rotated gradient of the epsilon converging to n of that epsilon of the epsilon. Okay. Okay, so this in particular, if this is 0, if you are sequence set of 0, then the sigma is 0 and we recover the previous result. Okay, so this is the kinetic formulation, and the idea is that you want to make an analysis of characteristics also for this also for these equations. The problem this source is quite bad source. Okay, so what we would in a certain way, very roughly speaking, is that if we allow the trajectory, so the characteristics to jump in the s direction, we can somehow integrate this source. This is very rough, but let me write precisely what can we get. We call Lagrangian representation. Lagrangian representation. Okay, for n belonging to a omega. Okay, so it is it is called Lagrangian representation. It is only a decomposition in characteristics. Okay, it is a decomposition in characteristics. So let me first write the space where the characteristics should live. They are maybe not the most standard one. So there will be cars on some domain, let's say E minus gamma, E plus gamma, with values in omega. Okay, let me say that this is contained in 0 t. In 0 t, with values in omega times r divided by 2 pi. Right? Okay, so there are 4 cars in this space where the equation is defined. And we assume that gamma x is Lipschitz. Then you will see that it will satisfy some characteristic equation. And we assume also that the component gamma x, let me write gamma equal to the 2 components, gamma x and gamma s. Okay, the first the horizontal component, gamma x will be Lipschitz, and this will be bounded variation. Okay, on the interval where it is defined. So these are the space where our characteristics will live, so the regularity that we require. Okay, then for every time belonging to 0, t, we consider the evaluation map. The evaluation map, it takes some curve and gives you essentially the curve evaluated at the time t. Okay. We would like to write gamma of t, since the boundary variation we choose a representative, for example, the right continuous one. Okay, and the definition of Lagrange representation characteristics. Okay, what it is a measure on the space of curves. So a positive measure plus here and finite. Okay, is a Lagrange representation. Lagrange representation of n. If let's say I of omega, if there are some properties. So the first one is that we have this condition that if we take the put forward through the evaluation map, so maybe this notation can be a bit heavy, but that explain L2 to get this measure, the Lebesgue measure is restricted to the space X M of N of e to the I is positive, which is just our old E Lebesgue. Okay, so what does it mean, this notation? It means that if we evaluate this measure, select a bunch of curves, okay, and we evaluate all of them at time t, okay? And what we get, the image will be essentially the set where t is equal to 1, okay? But this image is taken with some weight, and the weight is identical equal to 1. It is useful to work with this measure theoretic version because we don't have things defined everywhere. And so it is convenient to work with this measure theoretic, let's say. Okay. This is borrowed from the field of scalar transport equation, the linear equation. Is Ambrose did for the solution is this kind of representation for the solutions of the continuity equation. Okay, here the difference is that the transport part is very simple, the source is a bit more is a bit particular to this problem. This is just to say that this graph represents in some sense the solution. Then we want some other properties. So the properties is, for example, that they travel with characteristic speed. So gamma dot the horizontal component is e to the I gamma s of t. Okay, for almost everything. Almost everything, and this is exactly the characteristic equation because the characteristic speed is e to the I s. And then we have that the third property relates it's a way of decomposing also the measured sigma. Okay, like this characteristic will not be okay. I will just write this property. Okay, for I will take t equal to 1. It will not be in this. I will take t equal to 1. It is not applicable. Okay. And the total variation of our vertical components, gamma s, integrated with respect to this omega gamma. Okay, so in some sense, this you see that it's gamma s, the vertical component, and determine the speed of the curves. Okay, so if this total variation is 0, so it means that gamma s is constant. The speed is constant, so the characteristics are straight lines. It was the same as before. Okay, they are straight lines. If instead this total variation is not 0, then of course the characteristics now are Lipschitz function, by the horizontal component are Lipschitz, and they are not anymore straight. So this measure quantify how much this these trajectories fails to be straight lines. Okay. Okay. This is more or less the interpretation, and there is also a technical assumption that says that nothing is created or destroyed, no curves are created or destroyed inside the domain. They can be erased because they reach the boundary, or they have to be created because they start from the boundary. So if except if say T minus gamma is greater than 0, so we don't want to, it's not it's a curve which is created in the future, then the position must be.
Elio, just a question to understand. So assume M is smooth. So these gamma are the characteristics, or are the orthogonal, the flow orthogonal to the characteristic?
Okay, it depends on the S. There are both. It depends on the S, the kinetic variable. If everything is smooth, you have all of them. So at every point, you have M of X, and you have all the trajectories. Because they are curves there is one additional variable.
Right.
Gamma,
Yes.
and the X component will be all this direction.
Okay.
And this direction is selected by the vertical component.
Mm-hmm.
So indeed, at each point, yeah, people are there straight lines. The distribution is 0. You can take any of these entering trajectories.
Mm-hmm. Okay.
And they correspond to different S. Yeah, they are really characteristic for the kinetic formulation, characteristic for the equation. The same for the same let's say okay. And so this is what a Lagrange representation is. We have a decomposition and characteristic with these properties. And okay, if you want the proposition is that for every n belonging to A of omega, there exists a Lagrange representation. Okay, this I will not discuss. But once we have this, we can essentially give an interpretation, a quantitative version of the argument presented there. Okay, if you want, it is the same picture, but the problem is now that so here we have one, there's some trajectory. Now it doesn't need a straight line. Can we have another point here. We have another entering trajectory, selected by this measure omega. And then you would like to take another one. You would say that, okay, here we have a problem because you say if they are far from being a straight line, they dissipate. So they produce a lot of this measure sigma. And this sigma was controlled by our function. Okay, but the problem is that it's very easy to avoid one point. You just need to turn a little, very little. Okay? So you cannot really make quantitative this argument directly. What you should do is to consider a bunch of parts of parts all together, and with the same idea as before. Then you have all these directions, and if you are far from being a circle, okay, you will have that if you consider all the stars together, it is impossible that all of them avoid the others. Okay? So you cannot make the argument pointwise. This argument to consider these bunches of cards together, but then essentially you can repeat the argument there, make it significant. And what you get by this is that if you I draw the circle there. Let us denote by R of x1, x2, x3, the radius of the encircle. Encircle as above, okay, of the triangle obtained by taking the normals. Okay, what you can prove is that the integral of this r squared, okay, and you integrate on d omega all the triples omega, with h1 okay, this is controlled by so if you do this argument, what you get at the end is that you can control this geometric quantity. So how far are these three lines to be concurrent? An integral version by the measure of this kinetic, the mass of this kinetic measure. Okay, but now there is only geometric argument to say that this is actually control the left hand side, so the distance from the circle is in the statement. In this left hand side. And then we already said that the right hand side is controlled. Okay, here there is a geometric argument, it's unrelated from this problem. And so this concludes more or less. I don't know if